We're practicing for the first assessment in Unit 4, Topic 1. So this will cover lessons 1 through 4. The front side of your paper here, which I've rearranged the boxes, so yes, yours looks slightly different, but we're given a pattern of dots, stages 1 through 4. We are going to count up the dots, put it into a table, analyze that to see what type of function it is, and then make explicit and recursive equations. Also, we need to provide a graph. Okay. So, first thing I need to do is count up those dots, and I'll go ahead while I'm doing that and enter that into the table. So in stage 1, there's exactly 1 dot. In stage 2, we have 5. In stage 3, well, there's 3 rows that are 4 right here. So there's 12 plus 1 more makes 13. In stage 4, this rectangular array is 4 by 6. So there's 24 in there plus 1 more makes 25. So before we could go ahead and graph, I guess, but before we could do any equations or identify and explain the function, we need to know what kind of pattern we're looking at. So even though it doesn't say to show it, I'm going to show my first and possibly second differences. So this goes up 4, from 5 to 13 goes up 8, from 13 to 25 goes up 12. So I see a linear pattern in those first differences. I would also know then, or expect, and I can show here, that the second difference would be constant. So let's see, from 4 to 8 is up 4, and from 8 to 12 is up 4. So yes, I do know that this is, and I'm going to jump right now because I'm saying it anyway, to number 8, or pardon me, part E, which type of function represents the pattern. This is a quadratic function. And we know that because you could either say, you don't need both, but because the first differences are linear, or your other answer could be because your second differences are constant. Okay. Please don't combine those into one and confuse it and say that the second differences have a constant rate of change. That would absolutely be a lie. Okay. So first differences are linear, or second differences are constant. Well, okay, if we know that, we know how to write an explicit equation for this, and we do it using the quad reg. Okay, we're going to use quad reg to write this equation in your calculator. Now, just because I don't have a calculator here on the screen and it's fun for me, I'm going to go through for one time showing how we could do that explicit equation even if you don't have a calculator handy. Okay, so we first remember that it looks like y equals ax squared plus bx plus c. I can identify a couple of those things just from the table or my first and second differences, but there will be one value, and it's the variable b, that I'm going to have to solve for. Okay? So the a value is half the second difference. Okay? So this is half of the second difference. That means a is half of 4, 2. Right? The c value is the y-intercept. Now I don't have that in my table, but I can find it. If this is a linear pattern, counting by 4s, 4, 8, 12, the one right before that, right before I added 4, I must have added only 0. Right? That would fit into the linear pattern. Well, that means to get from the 0th stage, from stage 0 to stage 1, I added nothing. So that's telling me that stage 0 had to also be 1 dot. So the C is 1. Now, that looks like a lot more is missing than only the B, and that's because we can substitute in X's and Y's. You can use any of the points that you have, right, in your table. And 1, 1 is probably the easiest one, but I'm going to go ahead and use 2, 5 just because I think it'll be more obvious why I put each number where I did. If everything's a 1, and you look back at this, you might not realize why I put each one where I did. So if the point I'm using is 2, 5 for x and y, that means right here for y, I will substitute a 5. For this x, I will substitute a 2. Don't forget to square it. Plus, now I don't know the b, right? That's the thing I said we'd have to solve for. But I can put for this x also, again, a 2. So now we just solve for b. That's 5 is equal to, this 2 squared is 4, times another 2 is 8, plus 2b plus 1. Well, 8 plus 1 is 9, so 5 equals 9 plus 2b. Subtract the 9. Negative 4 equals 2b. Divide by 2. So b is equal to negative 2. So I do have all the parts I need for my explicit equation now. It would be either y equals or f of x equals. I knew my a was 2, 2x squared. I just found my b to be negative 2, minus 2x. And my c, my y-intercept, would be 1, plus 1. Now, if you really did that by hand, I would certainly feel a lot better if you were to take one of these points in the table and substitute it in and show that it really does work, right? Because that was a lot of confusing steps there. So let's say if I were to substitute in 3, I should get 13, right? So if I try f of 3, 2 times 3 squared minus 2 times 3 plus 1. So f of 3 is, 3 squared is 9, times 2 is 18. 2 times 3 is 6, so 18 minus 6 plus 1. 18 minus 6 is 12 plus 1, so 13. Yes, it checks out, it works. All right, let's write the recursive. So the recursive equation is f of, start with your first one, f of 1 equals 1. And then we do f of x is the previous term, f of x minus 1, plus, now we have to put an entire mx plus b expression here. It starts with the second difference, so 4 times x, and then we just try a point and adjust. Okay, that b there that needs to possibly, if anything, follow the 4x, comes from trying. So when I go from my first to second stage, I need to add 4. If I actually put 2 in here for x, so f of 2 would be your f of 1, which is 1, plus 4 times 2. Well, that means it would add 8. I don't want to add 8, I only want to add 4. So I have to subtract 4. Let's go through that again. If we were going from the second stage to the third stage, okay, that means your x is 3. To get to f of 3, you go back and look at your f of 2, and you add 4 times 3, that's 12. Well, I don't want to add 12 to get there, I only want to add 8. So I have to subtract 4 from that. All right, and lastly, we'll do this graph here. You're not going to be able to count by 1s. I think I gave you enough boxes that it would work if you counted by 2s, because we need to get our y value up to 25. All right, so x's will represent the stage. Y values will represent the number of dots. 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 2, 4, 6, yes, that would get us to 26. Just the 4 points in your table is enough. Now don't worry about the fact I counted by evens, by 2s, and each one of those dots then was in between because they were all odd numbers. That's fine. You still showed the pattern of the dots. On the back of that paper, we have one more big problem. This one's about Detective Nate. He's got 20 yards of caution tape to enclose a crime scene. I guess I should have put in a word there, a rectangular crime scene. So he wants the largest possible rectangle. All right, so draw 2 possible pictures of his crime scene. Well, how could we make a rectangle, make 2 rectangles that take 20 yards of caution tape? Well, if we're talking about the caution tape to enclose, that means that's our perimeter. All right, we need a perimeter of 20. So that means 2 lengths and 2 widths add up to 20, right? 2 times the length plus 2 times the width have to equal 20. Well, if we chop all of that in half then, what would 1 length and 1 width? Chop this in half, chop this in half, chop this in half. 1 length plus 1 width has to equal 10. So you come up with 2 sets of numbers that add up to 10. For example, this could be 2 by 8. This one could be 4 by 6. We have more possibilities, and that's what we're going to record in the table for part B. And I gave you exactly the right amount of rows for you to do each whole number side length. Now, that's not all the possibilities. There are infinitely many, because nothing says that we have to use whole numbers. But the smallest width, that's a whole number, would be 1, length 9. 2 would match up with 8, 3 with 7, and so on. So you just fill in every set of integers here that would add to 10. Now, after 5, 5, it feels like you're repeating, but you're now considering the length and width to be switched. Now, if those are your possible length and width, how do we get area? Well, area in a rectangle is length times width. So I need to multiply. 1 times 9 is 9. 2 times 8 is 16. 3 times 7 is 21. 4 times 6, 24. 5 times 5, 25. And then, since we were repeating the combinations down here, these areas repeat. And we're back to 24 and 21 and 16 and 9. Again, these are not the only possibilities. These are the integer possibilities. So we're going to graph, and we need to pay attention here. It's area versus width. All right? So we'll record our width as our x value and our area for the y value. Now, the greatest possible area in my table here is 25. I think there's 12 boxes here. Counting by 2s wouldn't make it. 3s would go over, but just in case you're uncertain whether or not that really is the maximum, let's go ahead and count by 3s. Okay? The width, I can count by 1s. Plotting these points, what are there? There are 2, 4, 6, 8. There's 9 points. We are graphing area and width, not length. So this length column, although it is significant, it has to do with how we got our area, but it doesn't go on the graph. All right, now once you have those 9 points there, we have to ask ourselves, do we connect them? Should this be a continuous graph, or should we leave it the way it looks now as a discrete graph? Well, it should absolutely be continuous. There is no reason whatsoever in anything on the paper that suggests we could not have a width of 1.5 and a length of 8.5. So we definitely want to connect these. But were you to stop at 1,9 and 9,9, you have forgotten infinitely many possibilities that exist between here. What if we had a really skinny rectangle where one of the sides was only 4 inches? Well, that is a possibility. So we need to extend those all the way to 0, 0, and 10, 0. However, we couldn't really have a width or an area of 0, so this should be an open dot. And same thing, we couldn't really have a width of 10 because then the length would be 0, so that is the actual perfect graph there. A continuous parabola that starts from 0, 0 and extends to 10, 0, but does not include either of those endpoints. Right. Make the equation. So again, you can use, well, this just says make one equation. We could either do explicit or recursive. I will do both. You don't need to do both. If you are doing explicit, remember you get that by doing quadratic in your calculator, or that long procedure that we used on the front side, or because we're familiar with how to do the area of a rectangle, you could actually do this one with your common sense or just with your math ability, all right? If we're making an equation with area and width compared, well, area, I'll use A of W is equal to, the way we get the area of a rectangle is we multiply our width times, now you do not want to use L for length to introduce a third variable in here. For length, think about, come back to this length column and ask yourself, where did you get each of these numbers? Once you decided the width, how did you know what the area, the length was that went along with it? Well, the length was always 10 minus the width. You knew that the one length and one width had to equal 10. So if we subtract length from both sides, width is just 10 minus, I'm sorry, if we go back to L plus W equals 10, if we needed an expression for length, we solve it for L, it's 10 minus the width. Okay, so this is a good answer. If you distributed that, A of W would equal 10W minus W squared. That's a good answer. If you used your calculator and you wrote y equals negative x squared plus 10x, that's a good answer. Now for recursive, I would want to start with, say, A of 1 equals 9, and then say to get A of W, I would do A of W minus 1 plus. Now, I would need half of the second, I need the second difference here. So I don't even have first differences on my table. I need to go back here and identify those. So this went up 7, up 5, up 3, 1, down 3, down 5, and down 7. So those second differences are minus 2. So the first thing I am going to put after my A of W minus 1 would be minus 2W. Now, I need to just see if it needs to be adjusted. So I go back and go, okay, well, how much, when I went from a width of 1 to a width of 2, so in these first two, I needed to add 7. If I actually substitute a 2 in here, negative 2 times 2 is negative 4. That's telling me, my formula as it is right now is telling me to subtract 4, but I need to go up 7. So that is very different. I need to add 11 to this. Let's do that again. If we looked from 2 to 3, well, what I really need to do is add 5. But if I substitute 3 in here, negative 2 times 3 is negative 6. Well, if it's telling me to subtract 6, but I need to add 5, to adjust, I have to say plus 11. Now, granted, this recursive one seems much more difficult. It is much more difficult than the explicit. So please, do that only if you are having no luck. You've tried the explicit and you just can't figure it out for some reason. All right, domain is the x values. And what x values are possible here? Or in other cases, what width values? Well, if you look at your graph, everything from 0 to 10, with the exception of 0 and 10, is acceptable, including all those decimals. Remember, we did a continuous graph, so that's everything from 0 to 10, not including 0 or 10. So do not include the or equal on those inequality symbols. What are the dimensions of a rectangular crime scene with the largest possible area? So 25 was the largest that we had in our table. Is that really the largest? Is that the vertex? And the answer is yes, it is. So 25 square yards is the largest. But there's a second question here. Oh, I'm sorry, this is backwards. That is the second question. The first question was, what are the dimensions of it? The dimensions means the length and the width. So the dimensions are 5 yards by 5 yards. And then the area is 25 square yards. Okay, but there are two questions there in that last box, so make sure you answer both parts.